Cell membranes. Cell membranes, the walled enclosure around a cell, are typically about T is equal to 7.5 nanometers thick. They are partially permeable to allow charged material to pass in and out as needed. Equal but opposite charge densities build up on the inside and outside faces of such a membrane, and these charges prevent additional charges from passing through the cell wall. We can model a cell membrane as a parallel plate capacitor with the membrane itself containing proteins embedded in an organic material to give the membrane a dielectric constant of about kappa is equal to 10. So here we have the positively charged plate and negatively charged plate. Here is the cell membrane, and the thickness of the membrane is 7.5 nanometers. Part A, what is the capacitance per square centimeter of such a cell wall? Part B, in its normal resting state, a cell has a potential difference of 85 millivolts across its membrane. What is the electric field inside this membrane? So the electric field will point from the positive charges towards the negative charges, and T is the thickness of this membrane. Now we have a dielectric material here, so we're going to replace epsilon 0, permittivity of free space, with kappa epsilon 0, the dielectric constant multiplied by epsilon 0. The parallel plate capacitor capacitance is then kappa epsilon 0, the area of each plate, A, divided by the distance between them, D. But here the distance between the plates is T. So A is the area, and permittivity of free space is 8.85 times 10 to minus 12 farads per meter. Okay, so we have the capacitance per area for this wall, C divided by A, is kappa epsilon 0, dielectric constant times permittivity of free space, divided by the thickness T. So that's the answer we're looking for. And if I substitute the numbers for capacitance per area, I have in SI units, the dielectric constant is 10, which is dimensionless. Then I have permittivity of free space, 8.85, 10 to minus 12, and 7.5 times 10 to minus 9 meters. That's nanometers, 7.5 nanometers. Now we're asked to find capacitance per area in farads per centimeter square. So capacitance per area is then 1.18 times 10 to minus 2 farads per meter squared. So if I convert that to centimeter squared, I will have 1.18 times 10 to minus 2. 1 meter squared is 10 to 4 centimeters squared. So this will give me, for the capacitance per area, 1.18 microfarads per centimeter squared. Now part B is asking the electric field inside this membrane. So in part B, the potential difference between the plates is the electric field multiplied by the thickness, as we have seen in the previous problems. So the electric field magnitude is the potential difference V divided by the separation distance T. So here I have an electric field magnitude. Because the potential difference is 85 millivolts, 85 times 10 to minus 3 volts, divided by the separation 7.5 10 to minus 9 meters, 7.5 nanometers. That gives me an electric field magnitude 1.13 times 10 to 7 volts per meter. All right, so we're talking about the cell wall again. It's basically a parallel plate capacitor. We have it's semi-permeable to charges, so we have a charge build up, positive charges on one side, negative charges on the other side, and it is filled with a dielectric material, organic material. Kappa is equal to 10. So for this cell membrane, we have the parallel plate capacitance kappa epsilon 0 A over T. Kappa is equal to 1 if it's filled with air, but it's filled with dielectric, so kappa is equal to 10. Epsilon 0 permittivity of free space. Capacitance per area is kappa epsilon 0 divided by T. We just substitute the numbers here to obtain the value for farads per centimeter square, so we find 1.18 microfarads per centimeter square. The electric field magnitude is the potential difference V divided by T, as we have seen in the parallel plate capacitor example previously. 85 millivolts is the potential difference, 7.5 nanometers is the thickness of the wall, so we find electric field magnitude of the order 10 to 7 volts per meter.